So this is an example in outer space. We have a satellite that has two solar panels, and the panels are initially wrapped around the satellite in this manner. So the satellite is a circular disk, a uniform circular disk, and the two panels are wrapped as two halves of a circular ring around the satellite. And the satellite is initially rotating in the clockwise direction with angular velocity omega naught. Now I'm going to, for simplicity for the algebra, assume that the satellite's mass is m and the total mass of the solar panels is also m, evenly split between the two panels. So the after picture would be after the deployment of these panels. So let's say the satellite comes in view of the sun and the panels need to be deployed to charge up the satellite's circuits. So I'll draw the after picture here. So this is going to be somehow deployed. Say it's got some springs. So that's the after picture. The various dimensions are going to be inherited from the original pictures. That's going to be the length, which is half the circumference of a circle, and the same with that because of symmetry. And also observe that the center of mass of these solar panels are going to be exactly in the middle. So that's again because they're uniform. And our aim is to find the final angular speed and possibly investigate if any energy was lost or gained in this process. So the first principle, the only principle that applies in this situation is angular momentum conservation. So we have to essentially set the initial angular momentum, which is the initial moment of inertia times the initial angular velocity, and set that equal to the final angular momentum, which is the final moment of inertia times the final angular velocity. So we are able to set these two equal, then we can solve for omega f in terms of I sub I and I sub f. So the next order of business is to determine I sub I and I sub f. The initial moment of inertia of the system is that of a disk and a ring. So you just go to your table of moments of inertia and grab the results from there. It's a disk of mass little m and a ring also of mass m, and the total there is 3/2 mr squared. The final moment of inertia is a little bit more involved because you have to remember that the parallel axis theorem has to be used for these two solar panels. Their center of mass is now located some distance away from the axis of rotation, and it's that distance d that we have to figure out. By just looking at it, you can see that d must be equal to r plus half of that solar panel length. So d is going to be pi over 2 plus 1 times r. So let's just proceed to calculate the final moment of inertia. That's just going to be the moment of inertia of a disk plus 2 of these parallel axis rods. So the standard entry in your moment of inertia table for a rod is 1/12 ml squared. So that's going to be 1/12 times the mass of the rod, which is m over 2, times the length of the rod, L squared. And then the parallel axis theorem adds a further factor of m over 2 times d squared. So let's simplify this a little bit. The moment of inertia of a disk is 1/2 mr squared. Now you observe that these 2's cancel out. So I'm just left with 1/12 ml squared. Well, L is equal to pi r, so that's pi squared r squared, plus md squared, where d is equal to that quantity. So it's going to be m times pi over 2 plus 1 squared r squared. This can be simplified. I'll just do a couple steps to see what I can do. That's 1/2 plus pi squared over 12. And what I can do there is I can expand this, because that's a plus b squared. So that's a squared plus 2ab. So if I do 2 times this times that, I'm going to lose the 2 there. So it's just going to be pi plus b squared, which is 1. And then mr squared comes out as a common factor. This 1/2 combined to give me 3/2. Now that's pi squared over 4, which can be written as 3 pi squared over 12. And 3 pi squared over 12 plus 1 is 4 pi squared over 12, which is pi squared over 3. So that's pi plus pi squared over 3. And clearly it satisfies our expectation that it's bigger than the initial moment of inertia, because the mass is more spread out once the satellite has deployed its solar panels. Let's put this into the conservation of angular momentum and see what we get. Li equals Lf. By the way, the conservation is about the z-axis, where the z-axis is coming out of the page. So that gives me II omega I equals IF omega F, and I can calculate omega F. Now let's substitute these values here. That gives me 3/2 mr squared divided by something bigger. 3/2 plus pi squared over 3 mr squared times the initial angular velocity. So the mr squareds can cancel out. And again, like I said, all this demonstrates is that it's moving slower at the end. So that is exactly what you will expect of a situation like this. Now, by the way, at night, when the satellite folds up again, it'll start spinning faster. So this should be compared to what happens in a figure skater's case. A figure skater on an ice rink, if he or she draws their arms together for a spin, they're going to keep spinning faster. And if they bring their arms out, they're going to start spinning slower. Well, ice has still got some friction, so this outer space example is even purer than the figure skater example. What about energy loss? Is there energy loss or energy gain? Now, to decide these questions in a easy fashion, I'm going to write kinetic energy in a special way. So let's first address that. Rotational kinetic energy traditionally is 1/2 I omega squared. Now I'm going to do the following. I'm going to write this as 1/2 I squared omega squared over I. I've done nothing illegal. I've multiplied and divided by an additional factor of I. But I times omega is the angular momentum. So that's L squared over 2I. Now this way of writing the rotational kinetic energy is very common in higher physics. And you'll see why it's really useful when we compare the rotational kinetic energy final over the rotational kinetic energy initial. It's just going to be Lf squared over 2If divided by Li squared over 2I sub I. Now by angular momentum conservation, Li and Lf are equal. The halves cancel, and then I'm just left with I sub I over I sub F. So the ratio of kinetic energies is equal to the inverse ratios of the moments of inertia. It's probably worth writing it. In this way, you can immediately decide if energy is lost or gained in a problem. If the moment of inertia increases, energy is what happens. If the final moment of inertia is bigger than the initial moment of inertia, this is going to be less than 1. So energy decreases. If the moment of inertia decreases, if the final moment of inertia is less than the initial moment of inertia, the kinetic energy is gained. So you can immediately say what happens. In this case, kinetic energy is lost, and the loss of kinetic energy can be accounted for by the energy spent by the internal motors getting the satellite to unfurl. For the figure skater's example, where the figure skater moves his or her limbs apart to spin slower, what happens there is you have to expend a certain amount of muscular energy to control your arm motions. You can't just let your arms fly out. It'll look undignified. So the figure skater will actually have to exert some inward force to get the arm to go out in a controlled fashion, and that's muscular energy there is what shows up as the heating of the figure skater's body when that happens.